This video is on confidence intervals for differences in means and proportions across two samples. You're not going to be tested on this semester, but there are several reasons why this is useful. First, there's lots of situations in practice where you might want to compare means or proportions across two samples, so it's useful to see the standard methods for handling this type of situation. Second, you'll see that the logic used to construct these kind of confidence intervals is exactly the same logic that we've been using up to this point. And so this gives you another opportunity to see that logic in use and to deepen your understanding of that logic. Lastly, at the end of the second video, I will do an example using a dummy variable as a way to look at differences in a mean across two samples. That's really one of the classic ways in which dummy variables are used. And so if that's still something that you're a little bit tentative about, this will give you another opportunity to see an example. To try to keep the videos from becoming too long, I'm going to break them up into two companion videos. In this video, I'm going to focus more on the sampling distributions and end up with the formulas for confidence intervals for difference in two means or difference in two proportions. And then in the follow-up companion video, we'll do some examples. So when we've been looking at the single sample or single population case, whether it's for the mean or for the proportion or for regression coefficient, we've always been starting with the point estimate, sample mean for the population mean, the sample proportion for the population proportion, the sample regression coefficient for the population regression coefficient. And these are important. They're important starting points, except they don't tell us how confident we should be. We don't know how accurate these point estimates are. We don't know how much sampling variability is involved, and so we don't know how confident or how careful or how cautious we need to be in terms of making decisions. And so what we need to add to our point estimates is a sense of what the margin of error is. Right? The margin of error may really help affect our decision making. And with the margin of error, we can construct a confidence interval. Well, how do we find the margin of error? Well, if we know the sampling distribution of our sample statistic, then we can calculate probabilities for different ranges of values for our sample statistic, and based on that, we can construct confidence intervals for mean, proportion, and regression. In all of these cases, we have the same exact logic and the same exact formula. We start with the point estimate and we add and subtract a certain margin of error. And that margin of error is just a certain number of standard errors times the standard error. How do we find those? Well, again, the sampling distribution for our sample statistic gives us everything we need. It gives us the point estimate, it gives us the standard error, and the shape of the distribution tells us how many standard errors we need to calculate in order to find the appropriate margin of error. But what about when we want to compare two samples or two populations? This comes up a lot in practice. For example, you might want to try to think about or understand better differences in average wages between two groups of workers, for example, union workers, non-union workers. So in that case, it's a difference in two means. Or as an example of proportions, right? Maybe we have some people in our organization who were hired early in their career and they went through our organization's career development program. And maybe we have other people we've hired later on in their career, so they've been external hires after the point at which going through a development program might have made sense. And maybe all of these individuals have been evaluated as to whether they're high potential or not, and so we have a certain fraction of employees in the organization who have been deemed high potential. And maybe we want to look and try to assess the effectiveness of our development program, and one way of doing that might be looking to see whether there's a higher fraction of people who are high potential in that group compared to the fraction or high potential in the external hires group. So in that case, we want to know, is there a difference in the two population proportions? Well, how can we go about thinking about differences in two means or differences in two proportions? So to start with the difference in averages, for example, we want to think about what's our best estimate of the difference in these two different wage averages. Well, if we just take them individually, we know that the best estimate of the mean wage among unionized employees is just the sample wage among our sample of union employees, and we know the best estimate of the population average wage among non-union employees is simply that analogous statistic in a sample of non-union workers. And so from that, it flows logically that the best estimate of the difference in two means at the population level is simply the difference in the two means at the sample level. And it's really exactly that same logic for for population proportions, right? The best estimate of each of these population proportions individually is the analogous sample proportion, and so therefore the best estimate of the population difference is just the sample difference. So in these two examples, if we wanted to better understand differences in average wages at the population level, our best estimate of that is difference is in the sample averages, and the same thing for the proportional case. Now, sort of unimaginatively, when we do this more generally or more generically, we're just going to talk about sample 1 and sample 2, or population 1 and population 2. So in that case, our best estimate of mu1 minus mu2 is going to be x bar 1 minus x bar 2. Our best estimate of p1 minus p2 is going to be p1 bar minus p2 bar. So, if we go back to the earlier confidence interval formula, the earlier confidence interval logic, this applies exactly in the same way to mu1 minus mu2 as well as p1 minus p2. So in those cases, whether it's mu1 minus mu2 or p1 minus p2, same exact thing as for mu, as for p, and for beta. Our confidence interval estimate of mu1 minus mu2 or p1 minus p2 is going to be of exactly the same form. We're going to start with the point estimate, and we're going to add and subtract a margin of error, which is going to be the product of the standard error of the sample statistic times the appropriate number of standard errors. And where are we going to find that information? Well, we need the sampling distribution. If we have the sampling distribution of x bar 1 minus x bar 2, that will give us the point estimate, standard error, and we'll know how to find the correct number of standard errors. If we have the sampling distribution of p bar 1 minus p bar 2, then we will have the point estimate, we'll have the standard error, and we'll have a shape of a distribution so that we can find the correct number of standard errors. And again, that will give us everything we need to find confidence intervals for mu1 minus mu2 and p1 minus p2. So let's take these in turn. Let's start with the difference in two means. So this is the sampling distribution of x bar 1 minus x bar 2. The mean of that distribution is just the difference in the two population means. The standard error might look a little messy, but the key thing here is that it's concrete and you can calculate it. This is the square root of the two variances from each sample divided by the sample size. Those are numbers that you'll be able to calculate from your sample, and so don't worry about where this formula comes from. Just notice that it's concrete and we can calculate a value. How about for the shape? Well, if the sample sizes are large, then just like in the single population case or single sample case, the differences in two sample means will have a t-distribution. Now there's two things here to focus on. First, it will have a t-distribution if the sample sizes are large. What does that mean? Well, in the single mean case, we needed the sample size to be at least 30. In the two population or two sample case, we need both sample sizes to be at least 30. So N1 needs to be at least 30 and N2 needs to be at least 30. The second thing that we need to look at is, remember, a t-distribution always has degrees of freedom. We always need to know the degrees of freedom in order to be able to use the right t-values. And so what is the degrees of freedom in this case? Well, it's the smaller of N1 minus 1 and N2 minus 1. Remember, in the single mean case, degrees of freedom was N minus 1. Here it's the smallest value, N1 minus 1 or N2 minus 1. And with that, we have the point estimate, we have the standard error, we know how to find the number of standard errors, and so we can use exactly the same logic for our confidence intervals. And the confidence interval is our point estimate plus or minus the margin of error. The logic for a confidence interval for a difference in two means or two proportions is exactly the same logic as a confidence interval for a single mean, single proportion, or a regression coefficient. So suppose that we have two samples. The smallest has 51 observations, and so then we know that the sampling distribution of x bar 1 minus x bar 2 has a t-distribution with 50 degrees of freedom, and it's centered at the difference between the two population means. And with 50 degrees of freedom, we can use our typical t table, and we can find with 50 degrees of freedom that for 95% confidence interval, for example, 2.5% in the upper tail, 2.5% in the lower tail, that's 2.009. That's what we have here. So we have 95% of our probability, 95% of the distribution, plus or minus 2.09 standard deviations or standard error. Here's the standard error. Because this is a distribution of x bar 1 minus x bar 2. This is the standard error of x bar 1 and x bar 2. And so remember our thought experiment. We take a random sample from population 1, a random sample from population 2. We can construct the differences in the two means. Maybe that's, say, here. And we can construct our confidence interval where we go up 2.009 standard errors, and we go down 2.009 standard errors from the difference in the two means. And notice that our true population mean difference here is within this confidence interval. Suppose instead we had gotten a different random sample from each population, and maybe we got a difference in means down here, something like this. And then we would construct our confidence interval by adding on and subtracting our margin of error from our point estimate here. And notice that our true mean difference is within that interval. Now, if we have a difference in two sample means that are way out here, then notice that our true population mean difference will not be within our confidence interval. Or if we have a difference in sample means is way up here, then again, notice that our true population mean difference is not within our confidence interval. But how often is that going to happen? We know exactly how often that's going to happen. 2.5% chance of being this far away on the positive side, 2.5% chance of being this far away on the negative side. And so with sampling distribution that looks like this for x bar 1 minus x bar 2 centered on mu1 minus mu2 with standard error that we can calculate from the formula given in the sampling distribution, then we can construct our 95% or whatever confidence interval plus or minus the requisite number of standard errors. And again, 95% of the time the true mean will be within that confidence interval. It's only 5% of the time when we're far enough away up here in this tail or far enough down here in this tail. There's only a 5% chance that our true population mean difference will not be in this confidence interval. Exactly the same logic as for a single mean or other confidence interval cases that we've already done. Turning to the difference in two proportions, so this is the sampling distribution for P1 bar minus P2 bar. The mean of that is the difference in the two population proportions. The standard error is shown there in box number 2. And again, similar to the previous case, don't worry about where this comes from. Just notice that this is very concrete and you can calculate it, or you could have Excel or some other statistical program calculate this. P1 bar is just the sample proportion out of sample 1 and the sample size N1, and then you can calculate 1 minus the sample proportion, and you can do the same thing in sample 2. So again, it might look like a mess. Don't worry about that. Just notice that it's concrete. It's known. We can calculate it. How about the shape? Well, similar to the single proportion case, the shape is normal as long as the sample sizes are large. What does it mean for the sample sizes to be large? Well, it means every cell size essentially has to be at least 5. So the fraction in sample 1 that is in the category represented by whatever your proportion is measuring, that has to be at least 5, and everybody in the other category that's not in whatever's being captured by the proportion, that also has to be at least 5. And the same thing has to be true in the other sample as well. Now, this is getting a little messier mathematically because we have two populations, but again, the logic is just the same. Don't let the math throw you off. It's only math. So with this, we have everything again that we need. We have the point estimate, we have the standard error, we have the number. We can find the number of standard errors, and so we can find a confidence interval as the difference in the two means plus or minus the margin of error. So to sum up, right, we have exactly the same logic, exactly the same approach for confidence intervals for means, proportions, and regression coefficient, and it doesn't matter in the mean or proportion case whether we have one sample or two. We're always going to center our confidence interval with our point estimate, and then we're going to add and subtract margin of error, and that margin of error comes from the sampling distribution. So don't try to see this as 5 completely separate different things. See the commonality, see the underlying logic. And whether we're looking at means or proportion or regression, one sample or two sample, the logic is all the same. So if you treat this as 5 different problems, 5 completely unrelated things, it can seem more overwhelming, be more of a struggle. If you focus on the logic, hopefully it just looks like 5 different applications of exactly the same logic.